Welcome. Right now I'm working on a graphical user interface that is built on FireSciPy. It is supposed to help with computing the reaction kinetics parameters for pyrolysis reactions. I would like to demonstrate here some of the work in progress. For now it specifically computes the activation energy of some pyrolysis reaction. It is a simple server that runs locally and you interact with it over the browser. I'm starting the app here from a virtual Python environment. Once the server is running, I can use this address to connect to it via the browser. On the top of the web page you see a couple of tabs that will guide you through the process of running the analysis. There's also messages shown on each of the tabs in case you have not provided the complete information in the previous tabs. First of all, I will create a new investigation by adding in some of the meta information. For this example, I'm following mostly the FireSciPy tutorial for the data processing of TGA experiments. The initial setup of the data structure that has been handled in the script like this is mapped into the web page here. Once I have filled in all the information that I'm interested in, I can just hit Create Investigation. And now you see here at the bottom the existing investigations with some of the information. Important is the label here because that is used to label all different investigations and files that are created later on. When hitting the X on the left, you can also delete different investigations. Now the different files need to be added to the data structure that the analysis can be conducted. On the web page, first we need to select the investigation where the files need to be attached to. We can select here if the temperature in the experimental data was recorded in Celsius or in Kelvin. In case it is Celsius, it would be converted to Kelvin because that is necessary for the computation. Here as the example, I'm using the same files that are used in the tutorial of FireSciPy. You can simply select the files and drag and drop them over here into this area. We see now a list with various files. It has detected the README file with an error because this is not the data file. Clicking on the X here on the left, we can simply remove it from the list. Now the next important thing is that we communicate what is the heating rate and the repetition for the individual experimental datasets. This app has some capabilities of guessing which values should be chosen for the heating rate and the repetition labels. Here the app has chosen a heating rate of 30 Kelvin per minute, which has been deduced from the file name. It has also chosen the R2 for the repetition label. In case you are unhappy with the choice, you can also change them manually here. Once you are happy with the information provided, you can add them to the investigation. In the next step, we would need to adjust the column mapping as some pre-processing step. The investigation needs to be selected again, and for the column mapping, the app is already guessing which column headers may fit to what we are interested in. It has determined here that the lowercase t would be for time, and for the signal we would use the weight. So I'm using signal here to distinguish between different data types. For example, from a TGA we would have primarily mass data. Using DSC data, the signal would be the heat flow. For the MCC, for example, the heat release rate. In case the app has not chosen properly, you can also remove the header and select from the available headers from the file a different one. But the weight was already a good choice. In the next step, the conversion range can be adjusted over which the assessment is supposed to run. Typical values would be 5 to 95% of conversion, but here the data is quite good, so I will expand it a little bit. You can also adjust the step size here if you would like to have a higher or lower resolution, or you could set a fixed count. Next at the bottom we need to select the data type. If you are using integral data, like from TGA, the mass data, or differential data, for example the heat release rate from the MCC. This has an impact on the methods that are used on the analysis step. Once everything is selected, we hit Start Processing. From the files we now get the conversion curves. This is here to allow you to inspect the data in case you may spot some errors. Now we are running the analysis, which is computing the activation energy. Again, we need to select the investigation from which we would like to analyze the data. Then we need to select the method that we want to use for this analysis. In this case, I have integral data, as discussed before, therefore I'm using here the Kissinger-Akira-Sonos method. Once selected, I can start the analysis. Now we can have a look at the results. Again, we need to select the investigation, and then we are provided with a couple of plots. Here on the left-hand side, the plot shows us the apparent activation energy plotted against conversion. At the bottom, we get the numerical results that are presented in the plots above. The first column gives us an overview over the conversion, the alpha, and the second column shows us the activation energies corresponding to the specific conversion step. These two columns on the left produce a plot on the top left. For each of the points, we also have some statistics that are computed and that are presented here too. We have the R squared, that should be 1 if we have a perfect fit, as well as the root mean square error, that should be 0 for a perfect fit. The data is provided in the two columns on the right. The isoconversional methods are based on linear fits that are produced between data points that are at the same conversion level but for different heating rates, means we have a shift in temperature. This is what we can see here, for example, in this pre-processing step. For increasing heating rates, the temperature at which a specific level of conversion is reached moves to higher temperatures. This can nicely be visualized with the lower edge of this bright box here at 60%. we can see that with higher heating rates, the 60% of conversion is reached at higher and higher temperatures. And when we conduct a linear fit through these points, we can now compute some statistics to get an estimate of how good the fit really is. The parameters of these linear fits, the slope and the intercept, are provided in these two middle columns. In this file also the points are available that have been used for the linear fits. They are just not shown here to not clutter up the whole page. In the last tab we can see these linear fits, or at least a couple of them, to get an understanding how the data actually looks like. Again, we need to select our investigation, and then we see the individual points. The circles of different colors are associated with the individual heating rates. Here at the top you can select different conversion levels. Again, this is just here to not overload the image. The dashed line indicates the linear fit for the parameters presented in these two columns. The next thing that we can do here on the result page is to download the CSV file, basically the file that is used to create the table here at the bottom. When we open this file, you see in the headers the conversion and the activation energy on the left, which is these two columns here. We have the R² and the root mean square error, again these two columns here. We have the parameters for the linear fit, these two columns, slope and intercept, and as I said before, also all the data points that have been used for this linear fit. The next thing that can be downloaded here is a Python script that can be used to reproduce this analysis. If you did find this video interesting so far, please hit the like button. Also, if you have some feedback in terms of how this app can be improved, please let me know. I'm now copying the content of the script that has been downloaded and put it into a Jupyter notebook. The only thing that I need to change is the path to where the experimental data is located. You will already see that the same information is provided here as you can see in the FireSciPy tutorials. For example, the initialization of the investigation skeleton. If you run the script now, it will also produce plots similar to the ones that we saw in the app before. For example, the activation energy over conversion, the one here on the left, the statistics with the R² and root mean square error, the plot on the right, as well as the overview over the different linear fits, the plot that is for now located in tab 6. Again, please let me know what you think about this application. I think the benefit really is that it allows one to run the analysis relatively straightforward and also get the Python script that then can be used for further analysis steps. Other than that, thank you very much and have a nice day.